Okay, so this is the lecture associated with Chapter 7 in the new book. So let's talk a little bit about conservative forces. So conservative forces are ones that satisfy certain criteria. And we've looked at two conservative forces so far. One is gravitational force. And the other one is spring force. Now, we've also looked at a non-conservative force a lot. So a non-conservative force example is friction. So one thing about conservative forces is that these are functions of position. And no matter where you are in the movement of the object within these force fields, within these forces, they stay the same at a particular location and in the same direction. So, if we think about gravitational force, it's always pointing downward. And in our case, we've looked at the situation where we've assumed that the gravitational force is constant, meaning that it's just a small change in height. But you could also do it for larger changes in distance when it comes to gravitational attraction. So just as long as it's the gravitational force is in the same direction at any point in the spatial domain of this object, makes it conservative. So if I go upward in the gravitational field, I'm going to do work in one direction, and when I go the other direction, I'm going to have work in the other direction. Okay. Now spring force is the same kind of thing. So you've got a spring. So as you compress the spring like this, at a given amount of spring compression, the force is going to be the same. So as I compress the spring, the force will become greater. And if I return to that same position, as far as the amount of spring compression, I'll have the same force and it'll be in the same direction. Now that contrast with that with something like friction. So here's an object that's going to slide on this surface, except that it's gotten stuck together there. So here's something that's going to slide. And so when I move this direction, so from left to right, the friction force is this way. But if I move this direction, the friction force is the other way. So in this case, there's a couple of reasons. One is because the force is not dependent upon its location in space. It's dependent upon whether it's moving or not, and also in which direction it's moving. So both of those things make this friction force a non-conservative force. So I'm going to dissipate energy when I move this direction. I'm going to dissipate energy when I go this direction. Whereas in a conservative force situation, I'll store energy this way and I'll unstore energy this way. I'll increase potential energy this way and I'll decrease potential energy the opposite way. So we've talked about these kinds of potential energy, and you can generalize to other kinds of forces, which could be force being constant, or force as a function of just a linear function due to spring. They could be any function of x. So what we can say kind of in general for conservative forces, this applies for conservative forces only. Is that the amount of work you put into an object is equal to minus the change in this quantity called U, which is called the potential energy. So up to this point, we've gotten, we have the potential energy can be the gravitational potential energy plus the spring potential energy, but it could be some, generic potential energy, whatever that generic value is, as long as the energy results from a conservative force. So if you remember here with the gravitational force, when we take an object and we move it upward against a gravitational field, so force of gravitation, so the displacement x is going up and the force is going down, that results in a positive change in gravitational potential energy. Now the amount of work that I do, the work, remember, is equal to the integral of F, the force vector dotted with the displacement, differential displacement vector. And so if these are going in the same direction, you get a positive work. So if the force and the displacement vector are in same direction, the work is going to be positive. And if the force and the displacement vector are in opposite directions, then the work is going to be negative. So in the case of this gravitational potential energy, my displacement is up, my force is down, so I get a negative work. And according to this, if I rewrite this as the change in potential energy is equal to negative the work, just multiply both sides by -1. So if I have this situation here with the gravitational field, that I'm going to increase the potential energy. In this case, specifically, I'm increasing the gravitational potential energy. Now the same thing kind of applies with spring forces. If this spring is being compressed, the force is going this way from right to left, and the displacement is going from left to right. So I get a negative work as I compress the spring. Negative work means that I have an increase in potential energy, which is what we said. We have an increase in spring potential energy when we compress the spring. Now when we uncompress the spring, the force is still going from right to left, but now the displacement is from right to left, so they're in the same direction. Therefore, work is positive, so the change in potential energy, specifically spring potential energy, is decreasing when the spring uncompresses. Now, if we look at just a small change in distance, so let's say this is delta x, and through this distance we have some force acting. So it's a force, and because delta x is small, we assume it's small, then we can assume that from an approximation standpoint that the force is going to be a constant during that small change. And we know that the work is going, if the force is constant, it's just going to be equal to force times the small displacement. So we said the work is equal to negative the change in potential, or the work is going to be equal to minus the change in potential energy. So not the minus potential energy, but minus the change in potential energy. Now if we divide both sides by delta x, we get that. And this is for a finite change in distance. If we apply calculus, we can show that the force is going to be the derivative of the potential energy with respect to x. And specifically, it's going to be the force in the x direction. So what this is saying is, if we have the potential energy as a function of x, to find the corresponding force that's being applied to that object, all we have to do is take the derivative of the potential energy with respect to x, and that'll give you the answer. Now you can kind of extend that to 3 dimensions. Here, this is just 1 dimension, but it turns out if you have some potential energy that's a function of x, y, and z, so it's a function of 3 variables, that the force in the x direction is going to be the derivative like this. But when you are doing this derivative in one direction specifically, you use this thing called a partial derivative and use a different symbol. So you take the partial derivative of this function of x, y, and z, and you take that with respect to x, and that would give you, and I've got to have a minus sign in there, would be the force in the x direction. And you could do the same thing. Y, you take the partial derivative of the potential energy with respect to y, and the force in the z direction is going to be minus the partial derivative of u, the potential energy, with respect to z. So let's just make up some function here. U is a function of x, y, and z. So let's say it's 2x squared plus 3y minus 4z cubed. So this is just a it's not really a surface in 3 dimensions, because the 4th dimension is this non-scalar or non-dimensional thing. But at a point in space, certain x value, certain y value, certain z value, you're going to be able to calculate the potential energy. And because this potential energy is just an algebraic function, or just a function, then it should be the forces that result in this are conservative forces. So the way you do these partial derivatives, so let's just show you how you do the partial derivative. So what you do is you do the derivative of this function as if the other variables, in this case y and z, are constants. So you'd have a constant here, and this would be a constant. Even though they're variables, but we're assuming they're constants to do this differentiation. So the only thing we'd have to take a derivative of is that part. These go to 0. The partial derivative of u with respect to y is going to be equal to 3, and the partial derivative of u with respect to z is going to be negative 12z squared. So that means that the force in the x direction at any point in space for this thing to be conservative is negative for x. So it's negative the partial derivative here. The force in the y direction is going to be 3. It's going to be constant. And the partial derivative, the force in the z direction is minus 3. If I got the negative sign. And here it's going to be negative a negative, so it'll be positive 12z squared. Now, one thing is, u is a scalar. So there's no direction, there's no I, j, or k vectors. But when you take the partial derivatives and the fact that they're equal to these components, the resulting components create a force vector. So what I could say is that the force vector is going to be negative 4x times I minus 3j plus 12z squared K. So that's kind of a cool thing that about these potential energy situations, is that the potential energy is scalar, but you can still get information about the vector nature of the whole arrangement by taking the partial derivatives and then multiplying each one of those appropriately by their unit vector in the three different coordinate directions. And so what we could do is we could say the force vector, instead of in terms of this specific example, it's going to be equal to the minus the partial, well, we could put the minus sign out in front of the whole thing because they're all going to be minus. So it's going to be the partial derivative of the potential energy scalar with respect to x times the I unit vector plus the partial of the potential energy scalar times j plus the partial derivative of the potential energy, or the potential energy with respect to z times k. And in the book they have this way of representing this as the gradient. It's this upside down delta is called the gradient, and it's a vector of u. And what the gradient is, the gradient vector says it's going to be equal to the partial derivative of something with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative of z with respect times k. And so this is called an operator. So when I do this, it's also called a del function, a del operator, or a gradient. What this does is it says take this scalar and take the partial derivatives of each of that function u with respect to x and multiply it by the unit vector I, plus take this u, take the partial derivative with respect to y. So it's not, I'm not multiplying these together. I'm saying let's do this partial derivative process on this scalar. So that's another way of writing this, is minus the gradient of u. And gradient is kind of like, you think of gradient as the, if you think about a mountain, and the grade is how steep it is, and the gradient operator is the derivative. And so what this is saying is, how steep it is it in one direction? Because, going down you have one steepness. If you're going around the mountain, you have essentially no steepness. So it depends upon your directionality of what the what grade you're doing. if you walk straight up a mountain, you're going to have one grade. If you go around the mountain like this, you're going to have a much smaller grade, and your gradient would be smaller as well. And they give you one example of the, kind of using this for the gravitational potential energy. Gravitational potential energy. So the gravitational potential energy is equal to mg times y. So if we have our coordinate system, x, y is up, and z would be this way. So what we're talking about, y is the elevation, the height. And you can see as y increases, as you go away from the Earth, here's the Earth. As you go away from the Earth, well, this probably should be closer. Let's move that up here. So you're on the surface. As you increase your elevation y, your potential energy goes up. So that makes sense. Now, to find out what the gravitational force is based upon this potential energy, you take negative the gradient operator of u. So that's going to be negative, and so you take the partial derivative of u with respect to x times I plus the partial of u with respect to y, partial of u with respect to y times j, plus the partial of u with respect to z times k. Well, the partial derivative of this with respect to x is 0, because when you're taking the derivative with respect to x, you treat all these as constants. The derivative constant would be 0. So for our particular case here, that's 0, and the same for the z direction, that's 0. So all you're left with is negative the partial derivative of this with respect to y. Well, the derivative of y is 1 with respect to y, so you just end up with mg. And then you multiply by the j vector. So what that says is that for a potential energy that's defined as such, that the force has to be negative mg, which is negative the weight. And that's what it is. The gravitational force is the weight of an object. So here's our weight, and here's our object. The gravitational the force that's acting on that body is going to be minus W, where W is the weight, which is positive. It's the mass times 9.8, positive 9.8, and then you have the negative sign, which shows it goes in the right direction. So your assignment, your questions for this, just 3 problems for this chapter. So it's 7.28, 7.31, and 7.33. So these all deal with conservative forces and work and potential energy.